Hi there, Andrew Dunkley here, and welcome to another edition of Space Nuts, episode 376. Coming up today, we're going to be looking at a rather incredible discovery, that of a distant, fast radio burst. Trouble is, we don't know what they are, or where they come from, or why. But, let's talk about it anyway. And back in 1952, some stars disappeared. Not the Hollywood kind, the real star-type sun things. But there's a little bit of a question mark over whether or not they ever existed. We'll also be answering audience questions about the speed of light, orbital attitude, and a lot more coming up on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And to tell us all about those things and much, much more is Professor Fred Watson, astronomer at large. Hello, Fred.
The original Space Nut. Yeah, I'm well, thank you, Andrew. All good. Still gasping at the wonders of the universe as always.
Yes, like everybody does. And otherwise no one would listen to us. So
No, they wouldn't.
And hi, Mum. We've got a fair bit to do, especially in the Q&A department later on. But let's start off with this incredible discovery of a distant fast radio burst. It's not only a distant one, it's the most distant detected to date. What's this all about?
Yeah, so the really interesting topic of the day, which has been a hot topic for about the last 5 or 6 years in the world of what we might call extragalactic astronomy, that's to say astronomy outside our galaxy, is a fast radio burst. I was once talking to one of your former colleagues, Andrew, on ABC Radio, and he said I was saying it wrong. He said it's actually fast radio burst.
Yeah.
Yes. He's right. He's perfectly right. It is, but it's too hard to say. So what are they? Well, they're basically millisecond long bursts of radio radiation that come from all over the universe. They're not from one particular place. They come from all over the universe. And we know that they are beyond our galaxy because some of them have been basically identified with distant galaxies. And you can actually measure the distance to the galaxy if you know that's where the fast radio burst came from, so you know how far that fast radio burst has traveled. And it turns out that's a really important aspect of this particular story. So what we're talking about is a fast radio burst that came in June last year. It was observed by the ASCAP radio telescope in Western Australia, Australian Square Kilometre Array Pathfinder. That's what the acronym stands for. And that telescope has actually shown itself to be a very efficient machine for discovering fast radio bursts. And so, there's a whole group of people who are tuned into analysing them. This particular research was led by a very good friend, Dr. Stuart Ryder of Macquarie University, who actually was with us in the UK not very long ago, sharing the load of the astronomy leadership of our tour. So Stuart and his colleagues observed this object. It rejoices in the name of FRB 20220610A, and that actually tells you the date it was observed. That must be the 10th of June 2022.
Right.
And so what they did was, because the ASCAP array is so efficient, they can very accurately determine where this burst came from. And that's the trick here. With the earliest fast radio bursts that were detected a few years ago, nobody really knew where they were coming from. It was only a few that could be identified with what we call host galaxies, a galaxy in which the object lies that caused the fast radio burst. But with this particular one, whose name I've just mentioned, but won't bother saying again. It was, as I said, it's a very precise determination of the direction in which that burst came. And so what the astronomers did was to use time on the very large telescope in Chile, the large set of 8.2 meter telescopes operated by the European Southern Observatory. We in Australia have a strategic partnership with the European Southern Observatory that gives us time on these telescopes.
Yeah.
And that's a 10-year partnership. So they used the VLT, the Very Large Telescope, to search for the source galaxy. And when they did, they actually discovered an interesting issue, because there were not one but three galaxies there. So it's a trio of galaxies that are at a great distance. They're actually what we in the trade call a redshift of 1. That means the light left its source in this trio of galaxies when the universe was half its present age.
Wow.
Roughly. So 8 billion years ago. So this light has been traveling from this very, very distant group of galaxies. And what they were able to do was kind of pin down which galaxy in the group it came from. That tells you how accurate the positioning was. But yes, so they were very excited when they realized that this thing was at this great distance. It was the oldest and furthest FRB, fast radio burst, ever determined, or should I say determined to date, because eventually something further away will be discovered. But there's a twist to this story, which is what makes it really exciting. And that is that when you observe a fast radio burst, what you get is this burst of radio waves, but it's if you're looking at many different frequencies in radio, which is same as looking at a spectrum of light, you find that the let me get this right, the higher frequency waves arrive slightly before the lower frequency waves,
right?
And that's because the radio radiation interacts with electrons in the universe. Now, for the fast radio bursts that were known back in 2020, that's 3 years ago, there were enough of them that what scientists could do was, if they could measure their position, their distance by locating or identifying which galaxy the fast radio burst was from, and you could do that for half a dozen or so, then what they could do was show that this dispersion phenomenon, the thing that stretches out the wavelengths of radio radiation, is proportional to the distance. In other words, the further away an object, further away one of these fast radio bursts is, the more dispersed its radio radiation is. The bigger the gap between the short wavelength and the long wavelength radiation. And that makes complete sense, because if what you're detecting here is a phenomenon caused by the passage of the fast radio burst radiation through this electron cloud that seems to permeate the whole universe, which we haven't really been able to measure before, then it's giving you insights into that matter within the universe. And in fact, back in 2020, a fairly young Australian astronomer, Jean-Pierre Macquart, working at Curtin University, I think, he demonstrated this phenomenon. And I can quote Stuart Ryder, who is going to put it in far better language than I just have done. Jean-Pierre was known to everybody as JP. JP showed that the further away a fast radio burst is, the more diffuse gas it reveals between the galaxies. This is now known as the Macquart relation. Some recent fast radio bursts appeared to break this relationship, but the new measurement, this is the big news, confirms that Macquart relation holds out to beyond half the known universe. And so JP's discovery back in 2020 was a real breakthrough, and what this does is confirms it in a big way, because you're stretching out the distance, as I said, to 8 billion light years. The sad side of this story, Andrew, is that JP, not long after that paper was published, he was only in his 40s. He died of a heart attack. Oh. Such a great shame for an astronomer who was kind of on the brink of he's already famous in the fast radio burst world, but sadly not able to enjoy that renown. Mm. So it's very, there's a very nice twist to this story. This new discovery shows that this matter, all these electrons are there. And a comment from one of the other authors of this paper, Ryan Shannon, who's at Swinburne University. Ryan says, if we count up the amount of normal matter in the universe, the atoms that we're all made of, we find that more than half of what should be there today is missing. And that comes from our understanding of the Big Bang. So what should be there is missing. But he goes on to say, we think that the missing matter is hiding in the space between galaxies, but it may just be so hot and diffuse that it's impossible to see using normal techniques. Fast radio bursts sense this ionized material. Even in space that is nearly perfectly empty, they can see all the electrons, and that allows us to measure how much stuff is between the galaxies. And so what they're going through is that basically, as Ryan Shannon says, while we still don't know what causes these massive bursts of energy, this paper confirms that fast radio bursts are common events in the cosmos, and that we will be able to use them to detect matter between galaxies and better understand the structure of the universe. So, big time stuff, and I find delighted to be able to mention it on Space Nuts.
Yeah, I find it fascinating because we don't know much about them. We don't know why they happen, but we can learn from them because we've come to understand what's happening with them, even though we don't know what's right.
It's
in the first place.
Right. It's absolutely right, and that sums it up perfectly. It's what made that first Macquart paper very special, because yes, you're taking a phenomenon that you really don't understand, but you're using it to sort of map the stuff between the galaxies. It's fantastic stuff.
Now, even though we don't know much about them, are they all the same thing? Are all fast radio bursts identical?
They're not, no. So even though what you've got is a burst of radiation which lasts no more than a millisecond, a thousandth of a second.
Yeah.
But quite often, if you sort of plot a graph of the radiation through that millisecond, it's got structure. It's got bits that show up earlier than other bits. And that differs from one fast radio burst to another. The current thinking is that what they are flares on the surface of highly magnetized neutron stars, which are called magnetars. That these things have flares on their surface, and that's what causes the fast radio burst. But you can then say, well, maybe you've got lots of different circumstances. These things might be rotating at different velocities. They might have a surrounding of other material, debris that's been emitted from them that the fast radio burst has to pass through before it leaves the magnetar. So that could explain why they're not all the same. But there could be even more fundamental differences. Some of these could come from quite different sources than others. So it is very much a hot topic at the moment.
And nothing akin to that of, say, the WOW signal that we've talked about before.
So I think the first 2 or 3 fast radio bursts attracted the attention of Avi Loeb, who is the director of the Harvard Smithsonian Institute for Astronomy, who always looks for the possibility of signals being of artificial origin. And he did speculate that for the first few, but I think that's gone quiet now. Nobody believes that they're artificially made.
Okay, so... And we still don't know what the WOW signal was. So, but
no, we don't. That's right. No, because that wow signal lasted for at least 70 seconds.
Yeah.
So it's very different from a fast radio burst. And you might call it a slow radio burst.
You might. Yeah. All right. Now, if anybody would like to read more into that revelation and the article that Fred referred to, it's at the ESO website, eso.org, and you can just search for the paper titled "Astronomers Detect Most Distant Fast Radio Burst to Date." It was published on the 19th of October originally, I think. But yeah, it's fascinating topic, and I reckon we'll crack it one day and figure out what this thing is, Fred. It was probably an alien ripping off a Band-Aid and screaming. That's what I reckon it is. Takes about a millisecond.
Well, it's happening all over. Yeah. It does take about a millisecond. You're right.
Yeah. Okay.
Quite so.
This is Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
Let's move on to our next topic, Fred. This doesn't date back 8 billion years, but or light years or whatever. It dates back to 1952, which is 71 years by my estimation. And this is a little bit controversial. This is about disappearing stars, or did they exist at all anyway? So, what do you reckon?
So, yes, your last paragraph, your last sentence there, did they exist anyway, is my being sceptical about what this is all about. So let me tell you what it's all about. Back in July 1952, the Palomar Observatory, which still operates the telescope, actually, what was called the Palomar-Schmidt telescope. Palomar is not far from San Diego in the United States, down there in California. It has, of course, the 200-inch telescope, which was for many years the biggest in the world, a 6-meter telescope, but also the Palomar-Schmidt. And the Schmidt telescope is one with a very wide angle of view, and one that can take photographs of large areas of the sky. And the idea behind building that Palomar-Schmidt, which was opened in 1948, if I remember rightly, was to basically provide a map of the northern sky that could be used for the bigger telescope to explore the most interesting objects. So they were doing this sky survey, and the technique was to take a photographic plate, which they were 14 inches square. I know all this because we have a copy of the Palomar-Schmidt in the Southern Hemisphere, the United Kingdom Schmidt telescope, and I used to be its astronomer in charge, so I know what operating a telescope like that is about. 14-inch square glass plates coated with an emulsion that's sensitive to light of different wavelengths. So what they did was during the night, as the night progressed, they'd take a photographic plate of the sky in one color, usually with probably first of all, I think with a kind of yellow filter or a reddish filter, and then another one with a blue filter, because getting the colors of stars, which you can do by that method, actually gives you hugely greater insights into what's going on with stars than just taking a plate in one color. So they took 2 plates, one at about 8:52 in the evening, and then another one not far off an hour later at 9:45, one in red light, the other in blue light. And when you compare them, there are 3 stars on the first one that aren't there on the second one. Yeah. So they've vanished apparently in a period of 50 minutes. And so there's a research paper which I've downloaded so I can look at the details, because there's a few details that I'd like to understand a bit better. But that paper is entitled "A Bright Triple Transient That Vanished Within 50 Minutes." In other words, three objects, 3 blobs of light on the plate that disappeared within 50 minutes. So the scientists who've written this paper are trying to identify what they are. One is a possibility that actually that's not 3 stars, it's just one. And what you've got is a star that sort of brightened up for a short time. But in between us and it, there was a black hole that caused a gravitational lens that actually turned the image of that star into 3. And we know that happens with gravitational lenses. We see that quite a lot in quasar astronomy. So you've got 3 stars that sort of disappeared 50 minutes later. That would be a very, very rare event.
Well, yeah, but the timing. I mean, what are the odds?
Everything. That's right. And I should say that this is not unique. There are other photographic images that show the same sorts of things, this disappearance. There's another idea that they weren't stars, that maybe they were something like cloud objects that, something made them brighten up or something like that. Oort cloud being that cloud of cometary debris that surrounds the sun. And a third idea, which I think is perhaps nearer the truth, nearer the mark.
Let me guess. A shonky photographic plate.
Well, that's kind of the direction I was going in. I'll explain why in a minute.
Okay.
But in fact, what they're suggesting is that because Palomar's not that far from where nuclear weapons were being tested, it's possible there could have been radioactive dust sort of blowing around and contaminating the photographic plates. And anything radioactive on a photographic plate is going to give you a bright spot.
Yeah.
So you got bright spots on some images and not others.
Okay.
So that's sort of what they suggest.
But what are you thinking? I mean, there are 3 interesting theories. The third one sounds like it does hold a little bit more water. But
yes, it does.
Yeah, could it just be?
So I think there's another possibility.
Itself?
Yeah, that's true. But I think the other possibility, and this comes from, as I was saying, the experience I had in doing exactly the same sort of work, but sort of 50 years later, with the United Kingdom Schmidt telescope, when we were doing photographic surveys of the southern sky rather than the northern sky. We did the same sort of thing, took plates with red and blue filters. And we were all well aware of a phenomenon on the plates themselves, which we called gold spot disease. And these were tiny spots, actually not of gold, it was silver, but it looked gold when you held it up to the light.
Yeah.
That looked for all the world like stars, but they were a contamination of the plate. In fact, there was some chemical reaction between the emulsion, which contains silver, the photographic process uses silver, and the emulsion and the atmosphere at the time that would kind of precipitate out this silver as little blobs on the plate. Mm. And so you've got a situation where perhaps there was gold spot on those original plates that does not show up on the other ones. And that would be fairly easy to detect if somebody just actually had a look at one of these plates. And I don't know whether they've done that because I haven't read the paper yet, or whether they've just used scans. If they've just used scans, you wouldn't be able to tell the difference between a star and a gold spot. But if you look at the plate, you can. It's quite obvious. So that would be my suggestion. But I will check with the paper to make sure they haven't done that. And one other caveat there, Andrew, is that the gold spots that we were familiar with in the UK Schmidt telescope photography, that was only visible in something that was called 3A type emulsions, which were relatively recent, very fine-grained photographic emulsions that actually came into use long after 1952. So those fine-grained emulsions weren't there. They didn't exist at the time those Palomar plates were taken. And I think it's fair to say that we only really saw gold spot disease in the 3A type emulsions, but there could have been other similar phenomena. As you said, a shonky plate, it's a sort of fault with the chemistry of the emulsion itself, and I think that's the most likely explanation. So
the stars never, ever existed in the first place?
Yeah, so they're just spots on the plate, but not stars.
Yeah.
Yeah.
Look, I'm looking at those images now, and I have what you would consider an untrained eye when it comes to these sorts of things. But looking at the spots that they suggest might have been stars, they don't look the same as the other stars that are in the image. The stars look like fuzzy little circular blobs, but the stars they're referring to that disappeared, they actually look a little bit more high definition, and they look almost square. So
they do, don't they?
I think that would have set off alarm bells instantly, wouldn't it?
You would, yeah, you would. I absolutely agree. That I noticed that as well. So I'll read the paper, and you never know, it might warrant a research article from Fred Watson, but that would be
never know, Fred.
The turn up for the books in this day and age.
Yeah. Does this happen a lot in astronomy, where you misread things that aren't there, or has it happened a lot over the years? Not just in these circumstances, but any circumstances where you're making observations of the same piece of space, and there's some inexplicable variation. Do you see that much?
Yeah. So, yes, you do. Well, that's right. So you get artifacts, not just in photographic plates, but in electronic detectors as well. And I think we've talked about some of them. You get, because cosmic rays filter down from the universe, they actually leave a mark on an electronic detector, on an image sensor. Usually the type we use are CCDs, charge coupled devices. So you've got this image that's got specks on it, and sometimes little straight lines on them. And you could easily be fooled into thinking they're real, but they're not. They're an artifact of the image. What you do it's a lot easier with an electronic detector than it was with photographic plates. You just take repeated observations, and then you can filter out all the stuff that comes and goes like that. So you can get rid of all those artifacts, but there are others as well. You sometimes get bright spots in detectors where there's a faulty pixel or something like that. If you don't know about that, you're in trouble. So yes, yeah.
So do you think the digital age has helped?
Yes, I think so. And maybe it may be that that astronomers who've come to this issue with the 1952 plates, with their sort of digital upbringing, have perhaps placed too much faith in the photographic plates, because they too had their blobs and specks and spots and things of that sort.
Okay. It's really interesting and worth a look if you want to compare the images and see if you saw the same thing that Fred and I have seen with those strange blobs. It's at the phys.org website. Just do a search for 1952 group of 3 stars vanished, and you should be able to find it. Space Nuts. Andrew Dunkley here with Professor Fred Watson.
Roger, you're allowed to clear here also.
Space Nuts.
Didn't I just say that? Yes. Now, before we get to...
It's an echo. It's an echo.
It is. It's an echo. Before we get to the questions, Fred, a little bit of homework from last week. We got a question from Doug in Idaho, who was talking about the carbon star La Superba. He was also asking about molecules in planetary nebulae, and you needed to do some homework. What did you find out?
Yes, that it's been known for many years that planetary nebulae do have molecules in them. Some really early work, actually going back to the 1970s, showed that there's abundance of simple molecules like H2, H2+, HEH+, OH, and CH+. And CH+ is not that far from methane, which is what we were talking about with Doug, I think, who raised the issue. Yes, so molecules can exist in the atmospheres of planetary nebulae. So the paper I looked at, which dates back, as I said, to the 1970s, is simply called Molecules in Planetary Nebulae.
Oh, that's handy.
Published in the Astrophysical Journal back in 1978.
There you go, Doug. Go look it up. I'm glad we were able to follow that up with for Doug, and it'll set him on a new course of discovery, I'm sure. Let's take an audio question now from Duncan in Weymouth.
Hello, Duncan here from Weymouth in the UK. A question about the speed of light and the start of the universe. Just wondering, is it potentially possible that there is a medium through which light could travel faster than what it does through a vacuum? I'm thinking about the period of inflation at the start of the universe when things are said to have expanded faster than the speed of light. Well, if potentially there could be some medium through which light could travel faster than it does through a vacuum, then this may explain that and may also have some, possibilities for future spacecraft traveling faster than light. I've no idea, but just a shot in the dark to see if anyone has looked into this, or is it possible, or is there some reason why people wouldn't look into this? I don't know. Just a thought. Keep up the good work. Thank you. Bye.
Thank you, Duncan. Apologies for the crackling. That was just something in the recording, but I just thought the question was worth investigating. Speed of light, the start of the universe, that period of inflation. The question basically was, do you think there could have been a medium that existed then that enabled light to speed up so that it was faster than what we know now as the speed of light?
Duncan's questions are always interesting, and this is a good one, and it's got a few little nuances to it. One is just to point out, which we've done many times before, that the universe itself isn't limited to the speed of light, because that Einstein speed limit of 300,000 kilometers per second in a vacuum is for stuff moving through the universe rather than the fabric of the universe itself, which can expand at any speed it likes. And so it means the period of inflation, which Duncan refers to, and yes, which is mind-boggling in how brief it was and how big the universe got in that, that tiny instant of time. That's whilst the mechanism for that inflation is not known, it's pretty certain that it did happen, and it's not really related to the speed of light. It's related to the energy input into the universe to cause that sudden and really very dramatic increase from, what is it, something the size of a billiard ball to something the size of a galaxy in 10 to the minus 33 of a second or something like that. It's just mind-blowing, as you said. But the constancy of the speed of light is in a vacuum is something that astronomers do work on, because fundamentally we believe that is an immutable constant of the universe, something that has never changed. Of course, the speed of light does change as soon as you put it into something else, like water or air or glass or whatever. The speed of light is lower. But to the best of our understanding, it never exceeds 300,000 kilometers per second. And part of the reason why we believe that actually goes back to the time of James Clerk Maxwell in the 1800s. In the middle of that century, he derived this property that came from the electromagnetic fundamentals that were known in physics at that time, and basically this speed of light kind of dropped out of that as something that cannot change. And effectively, it was Einstein who then carried that into his theories of relativity. And if you build in that the speed of light can't change, then it means that both space and time can. And indeed, that's what we observe. The changes that we observe in space and time, in gravitational lensing, in time dilation, they all exactly tie in with the notion that the speed of light is constant. A few astronomers have thought they've detected changes in the speed of light. One in particular here in Australia, John Webb, I've mentioned him many times before, looked at very distant quasars and thought he could see something in the spectrum that suggested that something was changing. This is at high look-back times. You're looking back again to kind of half the age of the universe. And he thought it's either the charge on the electron is changing, the electron, or the speed of light. But when you look at the data, and things must have moved on since I last looked at this, but it was very difficult to convince yourself that either of these things were real. And I think the astronomical community generally was skeptical about the any variation in the speed of light. So we've got no reason to believe that there was ever a time when light was traveling faster through a vacuum, or that there is some other state of the universe different from a vacuum in which the speed of light is greater. There's kind of no evidence for that in anything we've ever seen. And that's really the gist of Duncan's question, that was there another medium that we don't know about in which the speed of light is faster than it is in a vacuum? And we've got no evidence at all for that. So I suspect the answer is no, but it's a nice thought, Duncan. I like the way you think
it is. And Duncan will be as disappointed as I am that we are still no closer to developing an FTL drive.
Yes.
It still remains the realm of science fiction, Duncan, I'm sorry to say, but yes, too much energy required to achieve that, as we've discussed many times before. But interesting thinking, yes. Thanks for your question. Let's move on to a question now from Tom.
Hi, this is Tom again from Grimsby, Ontario, Canada. A few episodes back, you referred to the International Space Station as orbiting at an altitude of 420 kilometers. And I was thinking about what that really means. I assume the altitude is measured from the closest point on the surface of the Earth, corrected for sea level. What is the commonly used equivalent of sea level for other planets which don't have a sea? Does it even make sense to say something is orbiting Jupiter at an altitude? Also, altitude has another meaning for astronomers, being the angular distance from the horizon to an object in the sky. So talking about something orbiting at an altitude seems confusing. So if I were at a party having a beer with a bunch of astronomers and I wanted to fit in, how would I refer to the relative positions of a planet and its satellites or moons? Thanks again for a great podcast.
Thank you, Tom. I doubt that many astronomers have been drinking beer that have a nice Bordeaux or perhaps a Pinot water.
Oh, you've no idea, Andrew. No idea.
I probably don't.
A lot of astronomers I know and have known in the past will drink anything.
Okay. Real party animals.
Yeah,
oh boy.
Party animals, yeah.
Now, when it comes to aircraft, their altimeters are calibrated to sea level, aren't they? So, so when you're on the ground in Dubbo, it says that you're actually 260 meters above sea level at that time, or whatever it is in feet. So it's all relative. But when it comes to spacecraft orbiting the planet, how do they figure that out? Because as you orbit, the altitude would change relative to the terrain, wouldn't it?
It would, and it also changes relative to the orbit as well, because orbits are not circular; they're elliptical.
I was going to go to that next, but you beat me to it. That's fine.
Yeah. So the Tom's right that, and you are too, Andrew, that yes, you're passing over terrain at different heights. So I think when we loosely talk about the altitude of a spacecraft, we nearly always refer to it as the altitude height over the surface, and that would normally be related to sea level, exactly as Tom says. But the real number that you're interested in is not the distance to the surface; it's the distance to the center of the object that you're in orbit around, because basic orbit dynamics kind of collapses whatever you're going around to a single point, and this is the most elementary way of looking at it. And it's that distance from the center of mass, really, of what you're looking at to the spacecraft that is the really important thing. Now, that neglects the fact that if your orbit's too low, you'll hit the ground. So it's very good that we actually have the altitude above the ground as well. But yes, when people talk about the orbits of spacecraft around the Earth, they would talk about the aphelion and perihelion heights. In other words, the height when it's at its nearest, it's furthest from the centre of gravity of the Earth, and compare that with the nearest point to the centre of gravity of the Earth. So perihelion, I got it wrong. I said perihelion. That's for the Sun. That's in the case of the Sun. It's perigee. Perigee is the nearest point. Apogee is the farthest point for something in orbit around the Earth. And they talk about similar things on Mars. Apo Aries and Peri Aries. And Aries is the Roman name for Mars. And so that's the Latin name. And so you do the same thing there with, your heights. Rather than have an imaginary sea level, and there is actually an imaginary sea level on Mars, there is a kind of zero datum, which when you look at topographical maps of Mars that have been made by spacecraft like Mars Express and ESA spacecraft, you see that they've got the colours for the different heights above sea level, but there isn't any sea, so they've selected some given datum there above or below which the topography is measured. So it all comes into it. Tom's on the money there again. It's an interesting question, but if you think about apogee and perigee, that's a more important number, and that's probably what you'd talk about if you wandered into a bar full of astronomers or space scientists.
I suppose the other issue with sea level is because of the rotation of the Earth, we've got a bulge, so sea level isn't really a good indicator in terms of orbiting anyway. So it's all to do with dead centre.
That's where, that's right. That's where you would try and, that's where you basically locate things in the imaginary view.
Okay, very good. There you go, Tom. Hope that's solved your dilemma, or at least answered your question. Finally, Fred, this is a question that came on email via our website the other day. Hi, Andrew and Professor Fred. I was wondering whether Fred had met Dr. Elaine Maury at San Pedro de Atacama during one of his visits to Chile. He's completed the largest visual amateur telescope in the Southern Hemisphere and used an X-SPY satellite honeycomb mirror. Where did he get that, I wonder? If yes, details, please. And did you look through it? And what was the night sky like compared to Coonabarabran? Clear skies for Dubbo 2. Thanks, Andrew Broadhurst. Thanks, Andrew. So I guess question one, have you met him and did you look at his telescope?
The answers are yes and no. I'm interested in your comment there. Where do you get an X-SPY satellite honeycomb mirror? Probably from an X-SPY satellite surplus shop or something.
A disposal store.
That's right.
You never know.
Yes,
you never know where you're going to pick these things up, Fred, because I remember some people telling us that they had a table in their house in Mudgee that was from the HMAS Australia or something, or HMAS Melbourne.
I can believe it. At the risk of going down a rabbit hole that's unconnected, as a kid growing up in basically the years following the Second World War, as I did, there were government surplus shops everywhere, shops that were basically disposing of things that weren't necessary. And I used to hang around one of them interminably, buying bits of optical instruments so I could try and make telescopes out of them. So it's a big thing. But I do remember, and my brother can back me up on this because he used to hang around buying bits of electronics. We were once in that shop. It's in Bradford in Yorkshire, run by a man called Monty Passingham, if anybody remembers that in this Space Nuts audience. And please get in touch if you do. We remember Mr. Passingham actually selling a Lancaster airframe to somebody. So this was a World War II bomber. Yeah, he had the airframe parked at some airfield somewhere nearby, and he was actually selling it. So that's what you could do in those days.
I know. It just reminds me of something totally unrelated, well, sort of related to what you just said, but I saw somebody had developed a commemorative watch that's now for sale, and it's dedicated to one of Australia's Spitfire flying aces from the Second World War. The watch is actually made of parts from Spitfires of World War II. Can you believe that?
Yeah. Well, I can, and what I can't believe is that you haven't got one, Andrew.
Can't afford it. Can't afford it. I mean, they're not extremely expensive, but they're out of my league. Yeah. $10 will pull me up.
A Lancaster bomber was outside my league as well back in the day. Anyway, coming back to, I don't know, probably it may well have been restored or put in a museum. I've no idea what they did with it. What's most likely, Andrew, back in those days is that they cut it up and use the bits, use the metal in it. Yeah. Because there was nothing like the same imperative to preserve these absolute icons of history. Lancaster's played a big part in my family because my uncle, after whom I'm named, and I think I was his replacement, he was the pilot of a Lancaster that got shot down in the Second World War, and he's buried in a war cemetery in Hanover.
One of my school teachers in primary school was a bombardier on a Lancaster.
All right, yeah. There you go. So back to Alain Maurice. I'm sorry,
that was a great digression. I really enjoyed that.
I'm not apologising to you. I'm apologising to Andrew Broadhurst who asked the question. If I'd been apologising to you, I'd have called you Dave.
Yeah, probably.
Anyway, Dave, let's keep going. So I do know Alain Maurice. I can't remember where from, though, but I suspect he was visiting the United Kingdom Schmidt telescope when I used to work in that telescope here in Australia. I haven't met him in Chile. I have been to San Pedro de Atacama a number of times, but I didn't know he was there, and maybe he wasn't when I was last there. But next time I'm there, I will make sure that I get in touch with him, because I'd like to look through the largest amateur telescope in the Southern Hemisphere and see what an X-Spy satellite mirror does for you.
Yeah, I can imagine. To look at it. Have you actually looked at the sky from Chile in other telescopes, Fred?
I have, but they've all been small ones. What I've never done, and many of my colleagues have, including Stuart Ryder, who we were just talking about in connection with the fast radio burst, I've never used the ESO telescopes. So the Very Large Telescope or some of the other ones that they have, I've never physically gone there and observed with them. I have visited them, and checked them out and looked at what they're doing and things of that sort, but I've never actually observed with them. Of course, you don't look through them. You're always using electronic detectors. But I have looked through the sky from Chile with small telescopes, and to be honest, it is better than the conditions at Coonabarabran, but only if you've got a really big telescope. And that's because with a really big telescope, you start being affected by the turbulence in the atmosphere, which is much better in Chile than it is here in Australia, anywhere in Australia, actually.
There you go. All right. So it was a yes and a no, Andrew, but great question. Thanks for sending it in. And don't forget, if you have questions for us, you can do that via our website, spacenutspodcast.com, spacenuts.io. Both of those URLs work, and you can just click on the links to ask your question, the AMA tab or that purple thing on the right-hand side. I can never remember what it's called. Send us your voice question, I think it is, or voice message. But as long as you've got a device with a microphone, you are set. Don't forget to tell us who you are and where you're from. And while you're there, maybe check out the patrons page, and thank you to all our patrons. We don't thank you often enough for putting your money where our mouths are. We really do appreciate it. And check out the shop while you're there as well online. That wraps it up for another week. Fred, thank you very much.
Great pleasure, Andrew. Always good to talk.
All right, we'll catch up with you soon. Professor Fred Watson, astronomer at large, and thanks to Hugh in the studio for being Hugh in the studio. I'll say something nice just for a change. It won't last. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.